Welcome. We are going to start our second module in the fifth chapter. In this, we shall also discuss double integrals. First, we shall find the relation between integrability and continuity. In this module, our first target is to show that for a scalar field, continuity over a bounded rectangle in R2 implies its integrability. We start with the notion of span or oscillation of a scalar field defined over a set. Let S be a subset of Rn and F from S to R be a bounded scalar field. By span or oscillation of F over S, we mean the quantity span SF defined by supremum of Fx x from S minus infimum Fx x from S. It is easy to verify that if T is any non-empty subset of S, then span of F over T less or equal to span of F over S. First result, let Q equal to Cartesian product of the bounded closed intervals AB and CD and F from Q to R. If F is continuous over Q, then F is also bounded. Our strategy for proof is similar to the one we used for a function of a single real variable. Let us assume, if possible, F is not bounded over Q. Let us consider the four subrectangles A plus B by 2, Cartesian product with C plus D by 2, A plus B by 2 B, Cartesian product with C plus D by 2, and similarly the other two. Then F is unbounded in at least one of these four rectangles. Let us express this by Q1 equal to A1 B1 times C1 D1. Clearly, area of Q1 equal to 1/4 area of Q. In a similar fashion, we divide Q1 into four subrectangles of equal area. Then F is unbounded in at least one of these four subrectangles. We rename it Q2 equal to A2 B2 Cartesian product C2 D2. Also, area of Q2 equal to 1/4 area of Q1. We continue this process and thus we obtain two bounded increasing sequences An and Cn and two bounded decreasing sequences Bn Dn. Since Bn minus An tends to 0 as well as Dn minus Cn tends to 0 as n tends to infinity, by nested interval theorem we have limit Bn equal to limit An, limit Cn equal to limit Dn. Let alpha equal to limit An, beta equal to limit Cn. Then the point alpha beta is in Qn for every n. Since f is continuous at alpha beta corresponding to a fixed epsilon, there exists a delta such that xy is in open sphere with center at alpha beta and radius delta intersection with Q implies Fxy lies between the bounds f alpha beta minus epsilon and f alpha beta plus epsilon. This contradicts our assumption, thus f must be bounded. In a similar manner, we can prove the following result. Let Q equal to AB cross CD subset of R2 and f from Q to R be continuous. Then corresponding to arbitrary positive epsilon, Q can be partitioned into a finite number of subrectangles in each of which the span of f is less than epsilon. We shall use the above result to prove the integrability of a bounded scalar field over a compact set. Let Q equal to AB Cartesian product CD and f from Q to R be continuous, then f is integrable over Q. Since f is continuous on Q, f is bounded. Consequently, both upper and lower integral of f over Q exist. It remains to prove that they are same. Let epsilon be arbitrarily chosen. Since Q is compact, f is uniformly continuous. Hence, by the previous result, there exists a partition P which subdivides Q into n subrectangles Q1, Q2, Qn such that the span of f in each subrectangle is less than epsilon. Let small m r and capital M r denote the infimum and supremum of values of f x y when x y is in interior of Q R. Moreover, the sum over R area of Q R equal to area of Q. We form the following two sums: LFP equal to summation over R small m r area Q R and UFP equal to summation over R capital M R area Q R. We find that UFP minus LFP equals to summation over R capital M R minus small m r area Q R. This implies the difference between the upper and lower integral of f over q lesser equal to summation over R m r minus small m r area Q R, that is less than epsilon times area of Q. We obtain the desired result by letting epsilon tends to 0 plus. The next result helps us to find how to evaluate the integral of a continuous function over a compact set. Let q equal to AB cross CD and f from q to R be integrable over q, then integral over qf equal to integral c to d integral a to b fxy dx dy equal to integral a to b integral c to d fxy dy dx. Proof: let x be fixed in the bounded closed interval a b. We define capital A to be the set singleton x Cartesian product with C D. Then the restriction of f over A is continuous and hence integrable over A. We define g from AB to R by gx equal to integral c to d fxy dy for every x. Let x dash be from bounded closed interval a b. Then the difference between gx dash and gx is integral over c to d f x dash y minus f x y dy. This implies modulus of gf x dash minus gx lesser equal to integral c to d mod f x dash y minus f x y dy, and that is lesser equal to d minus c into mod f x dash y 0 minus f x y 0. Here we used ML formula to get this result. Y 0 is a point in closed interval C D where the function modulus of f x dash y minus f x y attains its maximum. The existence of y 0 is assured by the compactness of the set considered and continuity of f over it. Now, 0 lesser equal to limit of modulus gx dash minus gx when x dash tends to x. This lesser equal to limit x dash tends to x d minus c into mod f x dash y 0 minus f x y 0, and this is equal to 0 as the restriction of f over the set a b Cartesian product with y 0 is continuous. Hence, g is continuous at x. So, integral a to b gx dx exists and equals integral of f over q. Thus, integral of f over q equal to integral of a to b gx dx equal to integral a to b integral c to d f x y dy dx. The proof of the other part is in the same tune. In the following theorem, we show that the derived sufficient condition for integrability can also be weakened. Let q equal to AB cross CD and f from q to R be bounded. If the collection of all points in Q at which f is discontinuous has content 0 in R2, then the double integral f over q exists. Proof: since the function f is bounded over q, there exists a real number capital M greater than 0 such that for L x y in q, modulus of f x y is always lesser or equal to m. Let capital A be the collection of all points in Q at which f is discontinuous. By proposition, A is a set in R2 with content 0. So, corresponding to epsilon 1 greater than 0, the set A can be covered by a family of rectangles, sum of whose areas is less than epsilon 1. Let P be a partition of Q which contains these subrectangles of Q. Let q1, q2, qk be the remaining closed subrectangles of Q. Then f is continuous on each of them and hence attains in bounds in them. Let for every I in 1 to k, small mi and capital Mi denote the infimum and supremum of fxy when xy is in Qy. Let Q dash denote the union of all closed subrectangles of Q after Q1, Q2, Qk being deleted. Clearly, area of Q dash is less than epsilon 1. Now, we define two step functions L and U over Q as follows. Lxy is Mi if xy is in Qy and minus m if xy is in Q dash. Similarly, Uxy equal to capital Mi if xy is in Qy and otherwise it is capital M. Clearly, over Q, L lesser equal to F lesser equal to U. Since capital M is positive, we find that 0 less than area of Q dash less than epsilon 1 implies 0 greater than minus m times area Q dash greater than minus m times epsilon 1. Consequently, integral of U over Q equal to summation I from 1 to k Mi into area Qy plus m area Q dash lesser equal to summation I from 1 to k Mi into area Qy plus m epsilon 1. We can find a similar result for L, and integral of L over Q is greater than summation I equal to 1 to k small mi times area Qy minus capital M epsilon 1. Subtracting the second one from the first, we get that 0 lesser equal to integral U minus integral L less than summation I equal to 1 to k capital Mi minus small mi into area of Qy plus 2m epsilon 1. Since Q1, Q2, Qk are compact sets and f is continuous over them, f is uniformly continuous over them. By small span theorem, we can divide each of the rectangles Q1, Q2, Qk in subrectangles such that the span or oscillation of f over each of them is less than any pre-assigned positive term epsilon 2. With such a partition in hand, the above inequality transforms into 0 lesser equal to integral of U minus integral of f less than summation I equal to 1 to k epsilon 2 times area Qy plus 2m epsilon 1. Since integral of L lesser equal to lower integral of f lesser equal to upper integral of f lesser equal to integral of U, from the above we find that 0 lesser equal to upper integral of f minus lower integral of f lesser equal to difference between the integrals of U and L. This implies 0 lesser equal to upper integral of f minus lower integral of f less than epsilon 2 summation I equal to 1 to k area Qy plus 2m epsilon 1. Clearly, summation I from 1 to k area Qy lesser equal to b minus a into d minus c is a bounded quantity. The term twice capital M epsilon 1 arises from estimating the integral U minus L over Q, which is nothing but the difference of integrals of U and L from subrectangles covering A. The first quantity epsilon 2 times summation I equal to 1 to k area Qy come from the remaining k rectangles. Thus, we have 0 lesser equal to difference between upper and lower rectangle integrals less than epsilon 2 b minus a d minus c plus 2m epsilon 1. Letting epsilon 2 tending towards 0, the above reduces to 0 lesser equal to upper integral of f minus lower integral of f lesser equal to 2 capital M epsilon 1. As epsilon 1 greater than 0 is arbitrary and capital M is finite, we find that the upper and lower integrals of f coincide, that is f is integrable over q. Using this result, we also find the following. Let Q equal to AB cross CD and f from Q to R be a bounded function having a countable number of discontinuities. Then f is integrable. We have another result which is easy to prove. Let Q equal to AB cross CD and f from f and g both from Q to R be integrable. Then for every pair of real numbers lambda and mu, the function lambda f plus mu g from Q to R is also integrable. Moreover, integral of lambda f plus mu g over Q equals with lambda times integral of f plus mu times integral of g. Corollary. Let Q equal to AB cross CD and fg from Q to R be two bounded functions. We further assume that f is continuous on Q and g is identical with f over Q except for a set of measure 0. That is, g agrees with f almost everywhere on Q. Then g is also integrable over Q and integral of g equals with integral of f. We give the proof. Let us consider the function f minus g from Q to R. Clearly, it is bounded and the set of discontinuities of f minus g is a set of measure 0. Let us consider the function theta from Q to R defined by theta xy equal to 0 for every xy in Q. Now, theta being a constant function is integrable and integral of theta is 0. As f minus g and theta are different on a set of content 0, by previous theorem f minus g is also integrable over Q. Moreover, integral of f minus g over Q is 0. Now, f is integrable, so minus f is also. So, g equal to minus of f minus g minus f is also integrable. Consequently, integral of f over Q equals integral of g over Q. Till now, we discussed integrals of scalar fields defined over rectangles. Now, we shall discuss integrability and integrals of scalar fields defined over arbitrary sets which are bounded in a rectangle. We start with a result. Let gamma from AB to R be a curve. Then the graph of gamma is a set of measure 0 in R2. First, we recall that by graph of the curve gamma from AB to R, we mean the set collection of all ordered tuples T gamma T where T runs over A to B. Now, let epsilon be arbitrary positive number. Since gamma is continuous and AB is a compact set in R, it follows that gamma is uniformly continuous. Thus, by small span theorem, we can find a partition P of AB such that the span of gamma in each subinterval is less than epsilon. For each I equal to 1 to n, let us consider this collection of rectangles. The sum of area of the rectangles in the xy plane bounded by the lines x equal to xi minus 1, x equal to xi, y equal to infimum of gamma t where t is in xi minus 1 xi and y is supremum of gamma t when t is in the same interval. Clearly, the graph of gamma is covered by the collection of rectangles. The sum of area of these rectangles is sum I from 1 to n epsilon xi minus 1, that is epsilon b minus a. Since b minus a is a finite quantity and epsilon is arbitrary, it follows that the graph of a curve gamma can be covered by rectangles whose sum of areas is less than any pre-assigned positive quantity. Thus, gamma is a set of content 0. Now, let us consider a region Q by the lines x equal to a, x equal to b, y equal to gamma 1 x, y equal to gamma 2 x, where gamma 1 and gamma 2 are continuous over AB. Moreover, we assume gamma 1 lesser equal to gamma 2. Please look at the corresponding figure. So, Q is the region collection of all x y where x belongs to AB and y lies between gamma 1 x and gamma 2 x for each x. Clearly, Q can be covered by a rectangular region bounded by the lines x equal to A, x equal to B, y equal to infimum of gamma 1 x when x is in AB, say C, and y equal to supremum of gamma 2 x where x is in between A and B equal to D, say. We name this rectangular region Q tilde. Let f from Q to R be a bounded function. We define a function Q tilde from f tilde from Q tilde to R as follows. F tilde xy is fxy if fxy is in Q and 0 if xy is in Q tilde minus Q. Let df and df tilde denote the collection of all discontinuities of the functions f and f tilde respectively over their domain. Then d of f tilde is a subset of df union graph of gamma 1 union graph of gamma 2. First we assume that f is continuous over Q, that is df is the null set. Now both the sets Q and Q tilde are both bounded and closed, hence compact. Now the possible points of discontinuities of f tilde are the boundary points of Q. The set of all boundary points of Q has content 0 in R2. So f tilde is continuous on Q tilde except for a set of content 0. Hence f tilde is integrable over Q tilde. It is easy to notice that our discussion would follow the same track if we assumed f is continuous on interior of Q except for a set of content 0. The reason behind this is that union of finitely many sets of content 0 is also of content 0. Let us fix x0 in the open interval AB. That is, we consider the vertical line segment, say L equal to ordered pair x0 y, y lies between small m and capital M. The possibility is also there, it reduces to a single point. Clearly, it may be discontinuous at most at the points x0 gamma 1 x0 and x0 gamma 2 x0 in this. So, we have integral c to d f tilde x0 y dy equal to integral gamma 1 x0 to gamma 2 x0 f x0 y dy. Hence, integral over f tilde over q tilde equal to a to b integral c to d fxy dy dx equal to integral a to b integral gamma 1 x to gamma 2 x fxy dy dx. This implies integral of f over q equal to integral of a to b integral gamma 1 x to gamma 2 x fxy dy dx. This follows from the definition of f tilde. Thus, we have the following result. Let Q be a region in R2 defined as follows. Q equal to collection of ordered pairs x y where x is in AB and gamma 1 x lesser equal to y lesser equal to gamma 2 x, where gamma 1 and gamma 2 be two curves in R with domain AB and satisfying gamma 1 x lesser equal to gamma 2 x for every x in AB. Let f from Q to R be bounded. If the discontinuities of f in interior Q is a set of content 0, then f is integrable over Q. Moreover, integral of f over Q equals integral a to b integral gamma 1 x to gamma 2 x fxy dy dx. We cite an example here. Let Q equal to 0 1 cross 0 1 and we define f from Q to R as follows. Fxy equals to x square plus y square if x square lesser equal to y lesser equal to 2x square, otherwise it is 0. So, we can find the graph of the functions y equal to x square and y equal to 2x square intersect only at the origin inside Q. At all other points, the graph of y equal to 2x square lies above that of y equal to x square. We divide the region Q into three parts as follows. A is the region in Q where y less than x square, B where y lies between x square and 2x square, and C in Q where y is greater than 2x square. We ignore the border curves as they are of content 0 and does not affect the integral. We also notice that any vertical line segment in Q may not intersect all the three parts, but any horizontal line segment will do. First, we consider any fixed y in 0, 1, then integral 0 to 1 fxy dx. We divide the integral into three suitable parts. In first and the third, value of fxy is 0, so the only middle one survives, and we have calculated it. Then we integrated it once again, now with respect to y, the limits of integral being 0 and 1, and we have calculated. Next, in a slight variation to the above, we can also consider a region Q dash of the type Q dash equal to xy, where y is in CD and phi 1 y less or equal to x less or equal to phi 2 y, where phi 1 and phi 2 be two curves in R with phi 1 less or equal to phi 2. Clearly, the region Q dash is bounded by a rectangle AB cross CD, where A is infimum of phi 1 y, where y belongs to CD, and B equal to supremum of phi 2 y, where y is in CD. The existence of such A and B are assured together by the compactness of the interval CD and continuity of both phi 1 and phi 2. One can easily differentiate between this region and another discussed earlier. In the first case, if we consider any vertical line, it crosses the boundary of the region of integration at most twice. No such guarantee can be provided for horizontal lines. The case is just the opposite for the second one. If f from Q dash to R be bounded and the set of discontinuities of f in interior of Q dash has content 0, then proceeding as above, we can find that f is integrable over Q dash. Moreover, integral of f over Q dash equal to integral C to D of integral phi 1 y to phi 2 y fxy dx dy. We give an example here. Here we have to evaluate integral x dx dy over the region bounded by the line y equal to x and the circle x square minus 2cx plus y square equal to 0, where c is non-zero. We can easily find that here the region is bounded by the line y equal to x and the circle x minus c square plus y square equal to 0. That is a circle of radius modulus c with center at C0. First, we assume that c greater than 0. We can find the adjacent figure. From this, it is clear that the region of integration is bounded by the lines y equal to 0, y equal to c, x equal to y, and the curve x equal to c minus root over c square minus y square. Then, integral over q fxy dx dy we have calculated and found that it is c cube 2 by 3 minus pi by 4. Next, let c be less than 0. Then from the adjacent picture, it is clear that the region is bounded by the lines y equal to c, y equal to 0, x equal to y, and the curve x equal to c plus root over c square minus y square. Here also we can evaluate the required integral. We have calculated it here. Looking at the above example, one can easily understand that it can be solved another way. That is, if c greater than 0, we can treat the region of integration bounded by the lines x equal to 0, x equal to c, y equal to x, and the curve y equal to root over 2cx minus x square. For c less than 0, the bounds are x equal to c, x equal to 0, y equal to square root 2cx minus x square, and y equal to x. Thus, we have integral over q fxy dx dy equals integral from 0 to c x root over 2cx minus x square dx, which may not be so easy to calculate as the earlier one. One remark here: in case the region of integration is bounded by a circle or an ellipse, or in general a bounded region such that every vertical or every horizontal line intersects the boundary at most twice, we can change the order of integration. This helps us to make our calculation easier. In such a case, for some integrable function f from q to r, integral of f over q can be calculated using formulae like integral a to b integral gamma 1 x to gamma 2 x fxy dy dx, which equals with integral of f over q, which is again integral c to d integral phi 1 y to phi 2 y fxy dx dy. In such cases, the order of integration does not matter. Let us consider the integral 1 to e integral 0 to log x fxy dy dx. We suppose that f is integrable over the region mentioned. Here the region q is bounded by the lines x equal to 1, x equal to e, both are vertical lines, then the horizontal line y equal to 0, and the curve y equal to log x. We can easily check that every vertical or horizontal line intersects q at most 2 points. Changing the order of integration, we find integral of f over q is integral 0 to 1 integral e to the power y to e fxy dx dy. As in closed interval 0 to 1, the inverse of y equal to log x is x equal to e to the power y. With this module comes to an end. In the next module, we shall discuss Green's theorem.